in a level surface drag question, there's about 3 or 4 different ways this problem can be presented. I'm going to give you several of what I think are the question types and usually how they describe the problem and the setup for the problem. And I'm going to give you a couple ways to earn points. But ultimately, if you want to get an A on the next test, you will have to be able to solve one of these to its conclusion. But I will also tell you the stop points where, if you can do it at least up to this part, you'll get a B, stuff like that. So we're going to assume that there's a section of ground where there's no friction and then a section of ground where there's some kind of friction. And the green area represents the part where there's a frictional force of some kind. So these problems generally start on level ground. They're going to ask for probably a free body diagram for when the box hits the green surface. And almost always these problems will be broken up into 2 parts, with the first part being standard friction, where there's going to be some coefficient of kinetic friction. And that one's easy because that's going to have an acceleration that is constant. And because there's an acceleration that is constant, you can use Galileo's motion equations, or you just use F equals ma to derive an expression for the acceleration. And from there, you can usually figure out how far it goes, how long it takes to stop, stuff like that. These are very basic problems from the first semester. But then they'll go to part B, where they will change it up. And they'll say that there is a frictional force or a drag force or some kind of surface that intones a force that is proportional to the velocity. They may or may not put the negative sign in there. It's implied that this force is trying to stop the object. It's going to be in the opposite direction of the velocity. So the moment you know that, and these are, remember, velocity-dependent forces. This whole unit that we're talking about is going to be velocity-dependent forces. In all of these problems that have a velocity-dependent force, you cannot use your Galileo's motion equations anymore, because your acceleration affects the velocity, and therefore the velocity in turn affects the acceleration. So you're going to have to find a different way to solve them. And the only way that we're going to be trained on is solving a straightforward or maybe a less than straightforward differential equation. So usually the same kinds of rules will apply, meaning that they're going to ask for something like a free body diagram. So you should indulge them with a nice, straightforward free body diagram. I gave a test in AP Physics 1 last week. And in that test, so once you got your free body diagram, you're going to be asked, and this problem, they can ask it a couple of different ways. I'm giving you the phrasing, and there's a reason for it, because I want you to understand that they're going to give you a clue. So usually the clue is something like this: write an expression for a differential equation that could be used to solve for the velocity as a function of time. Write an expression as a differential equation that could be used to solve for the velocity as a function of time. So for some of you, that's going to be distracting, because you're not going to understand, what do you mean velocity? They're talking about something else here. They're talking about forces. You have to understand, the moment they say that, and they may not even say differential equation, but when they say that you need to solve and create an equation for the velocity as a function of time, you have to start with net force equals ma. So it's all you have when it comes to forces. And there are ways to get to velocity that aren't through differential equations, like energy. And so you can do the work energy function. But again, you have a force that is dependent on the velocity, so you can't actually calculate the work. Not using something like this. This is calculating the force as a function of displacement. You have nothing of the sort here. So you have to be careful, but they're going to give you the clue, and the clue is the word differential equation and expression for velocity as a function of time. Those are your clues that you're going to do this. They might even say in that thing, do not solve it. Fine, great. You're going to get points for just writing an equation down. You're not done quite yet, but we're almost there. First thing I want you to recognize is that you have to deal with the net force part, and you guys tend to forget these are vectors. So one of the first things you should do is make sure you are paying attention to direction. I would make your velocity the positive direction. I would make your velocity the positive direction and pay attention to the directions of your forces. By making the velocity the positive direction, you are making this force negative. And oftentimes there will be a negative in the equation as a clue that this force opposes the direction of motion. So when you write that in there, make sure you put in that negative sign. So the first part, of course, is just putting in your forces, whatever they happen to be. The second part is making it a differential equation. You have one substitution to make. So you write the differential form of acceleration. The moment you've done that, you've solved what they've asked for, or you've given them what they've asked for, right? But do not solve a differential equation that could be used to find the velocity as a function of time. That's this differential equation. Because right here, this says velocity as a function of time. It's right in the differential. Now, usually part B is now solve that equation. So we have to do the rest of it. Now, when they say solve the equation, oftentimes they will give you the answer, meaning they will tell you what the equation is supposed to look like. They don't care that you can derive it all the way. They care that you understand the process to get there. But often, if they give you the answer, that's because it's going to be used later in the problem. So if they give you the answer, you're not going to get a point for finding it. You're going to get a point for setting up everything you have to do to find it. Does that make sense? Now, if you want a C on your next test, you need to be able to set up the differential equation. All right, that's C-level work. It's a single substitution. But if you want a B on it, you need to get this all the way to something that can be integrated. So let's talk about the steps to do that. We've done this before, but I'm going to go back through the steps. We're going to use the process of splitting the derivative. We are not going to use the process of guessing at an answer, but we could. We did it once before, but this is a process and it works a little bit better. So we are going to split the derivative, and I'm going to go through each of the steps. You probably will only get 1 point for doing this whole process, getting it to the integral, but getting it to the integral is important. So here we go. Step 1. You want to isolate your derivative. You don't have to do this step. I like doing this step, though, because I think it makes future parts of this problem easier. So isolate your derivative. The next one is actually doing what the process says. You have to split the derivative, which simply means multiplying by whatever the denominator of this fraction is. So we're going to multiply both sides by dt. Again, this is the split part. Now, I'm trying to make this a little bit generic because there's no telling what differential equation you may actually have to solve. But this side has the t portion of the problem, and this side has the v portion of the problem. But whatever your derivative is, your next step is to collect terms. So whatever's on the derivative part on the left side, you need to get all of those variables there. So on the left side is a t, so you have to find every instance of t in your problem and make sure it's on the left side of the equation. There are no instances of t, so I don't have to worry about it. On the right side, it's dv. So you have to find every instant of v on the problem and get it to that side of the equation. So in this case, we're going to divide both sides by v. So collecting terms. Now, at this point, we're in a position to integrate both sides. And that simply means drawing your fancy little integral symbol. But you won't get points for just drawing the integral symbol until you do the next part, because we're setting up our integral here. And our next part is important. When you're setting up the integral, you have to, and a bunch of you are in calculus, and calculus is going to do this a little different than we are, although you can do it the way you were trained in calculus. I would like you to do it the way I'm suggesting for you, okay? In calculus, you would leave this probably as an indefinite integral. And when you do that, you will integrate both sides, and there'll be a constant that you'll add at the end of your integration because it's an indefinite integral, and then you'll put your boundary conditions in to figure out what that constant is. We will close our integrals and make them definite integrals by putting our boundary conditions in right now. The boundary conditions are almost always going to be your starting condition, whatever the starting condition was. So it's not hard to do this, but it's something that you have to be cognizant of. They will be looking for this. This is how you earn the point for setting up your integral. It's not by just drawing the s. It's about putting in your boundary conditions. And we have one. The first boundary condition is what you started at. We started at time 0 with a velocity of v naught. That's our boundary condition when we started. Now, keep in mind, if you did not make v the positive direction, you would have to make that negative v naught. That's why that's pretty late in the problem. A lot of people forget that, which is why I usually want you to deal with your vectors as soon as you can, so you don't have to worry about them later. Now the next step is you have to put your top conditions in. Your top conditions will be whatever this variable is. You just put that at the top, because we are creating an equation. So our top ones are going to be the variables of our problem. Now you just integrate each side. You actually do the calculus to get there. But if you can get to this point, you can set up your integral, then you're probably going to be able to get a B on our next test. Yep. Suggest. We'll take out the negative c over m, and that leaves us with the integral from 0 to t of dt. We'll just do one side at a time, all right? So let's do this part. When I take out the constant, I'm left with just dt in there. What is the antiderivative of nothing? Yeah, in this case, there's an implied t to the 0 power there. So I add 1 to that exponent and divide by the new exponent, and I'll just get t. So this is going to be c over m t evaluated from 0 to t. Well, evaluating this from 0 to t just means putting in the top boundary and subtracting the bottom boundary. So this is c over m times t minus 0. But I'm going to leave out the minus 0 if that's all right with you guys. All right. Let's do the right side. What's the antiderivative of 1 over v? If you don't know that, you have to memorize it, but it's also on your equation sheets if you don't. In fact, any integral that you will need for your exam will appear on your equation sheet. So if you need an integral and it doesn't fit this form, check your equation sheet. It's going to be on there somewhere. But we'll learn the process. This one is the natural log, so it's not tough. It's natural log of v evaluated from v naught to v. Now, you guys know rules for natural logs, but in case you don't, we're going to talk about them a little bit here. I'm going to go ahead and put in my actual variable here. You can't take the logarithm of a negative number, so that's why the bars are there, not parentheses. It's the way I was trained. You have to put that there, but we're dealing with physical quantities anyways. So generally, if you are doing something in physics and a negative has to appear there, you've made a you've made a mathematical mistake. You need to figure out where your mistake is, because you can't take the logarithm of a negative number. We need to solve this for v, and the log of v naught is a constant. We could do it right now, but it is almost always better if you have logarithms that are being subtracted to collect them. So I would always encourage you to collect them when you can, because you're going to get rid of that logarithm, and the only way to do so is to raise both sides of this to a base of e. So try and collect your logarithms if you can. It works out okay at the end, but most of you don't have good grasp of logarithm rules, so it's better if you can collect it and only have one thing to take the anti-log of. Raised to the base. So that is the calculus right to here. And again, the next part of this is algebra. It's not calculus, but we still don't have an answer yet that would be acceptable, and it definitely won't match the form of what's there on the test. So your next part is, of course, to get v isolated. So most of you who have had calculus know exactly what to do next. We raise both sides to a base of e. And then it's real easy. Just solve. Some things to keep in mind, though, once we get here. Check your units. Make sure it makes sense. So right now, if you have anything in an exponent like this, those units better cancel out to be nothing, because there should be no units up there. So that should be a unitless quantity. But we don't know what the units of c were. We could probably figure it out, because we know that it was a force that it was based on, and we multiplied c times the velocity, so we can probably figure out the units for c. But the important detail here is that when you take the exponential here, that's going to leave you with a unitless value. So the only units are those that are buried here. So that makes sense that we have v equals v naught times something, because that means we're going to have something that's in meters per second. The next thing, however, is, does it match up with your boundary condition? If you want to check your algebra, check your boundary condition. So our boundary condition is that our velocity was v naught at time equals 0. So put in time equals 0 and see if you get v naught. This is just checking to make sure your math works. So when I raise e to the 0 power, I get 1. And 1 times v naught is v naught, so it checks out. So I would always encourage you to check your boundary condition. That verifies your math. Now, they probably will have given you the answer, but there'll be more to it because they'll probably have other questions to ask about this. For example, does this thing ever actually stop? Technically, you guys would say no, right? But on an infinite time scale, it does. Now, we have this. There are other things you can figure out, and you should be aware of it. How far does the object go before it stops? That's an answer you should be able to ask because you have velocity. And the moment you have velocity, you also have a way of figuring out position. So keep in mind, you're not generally done just because you have an expression for the velocity, because you can now do it again to get an expression for position. In fact, try it. This should be one that you could be successful doing. Most of you know how to do this one. See if you can figure it out. Let's give it a try here. I'm going to split the derivative. I'm going to collect terms. I don't have to worry about that too much. They're already collected. I'm going to integrate both sides. I'm going to take the antiderivative of both sides, or integrate both sides, however you want to say that. Left side, I'm going to x minus 0. Right side, well, I'm going to u sub, which means I'm going to put u equals negative c over m a t. I'm going to take the derivative of that and find that du with respect to t is negative c over m. So dt equals negative m over c du. This is a standard thing called u substitution. I don't do it necessarily the standard way you're supposed to in calculus. So the only difference I do is I kind of strip away my boundary conditions while I do this, even though I'm not supposed to. I plug in all the things so I get something in terms of u. And again, if you have to take this integral, there will be an integral table that has this exact integral on it, not with c over m, but just some other constant. And you would plug in the constant. But we'll do this anyways. Pull out my constants, v naught, m, c, and a negative sign. And in my integral is e to the u du. What is the antiderivative of the exponential? Just the exponential. But I'm going to plug back in what I had for u, and I'm going to evaluate this from 0 to t. All right. If you're able to make it to this point, or at least follow along to this point, I want to impress upon you two things. First, there will be an integral table as part of your equation sheet. You should already know that because I gave you the equation sheets, and there's an integral table on them. That's what I was saying before I was so rudely interrupted by one of my students, Daniel. Now it's in the video, so somebody can watch this later and hear me say this about Daniel. We were talking about the fact that there's an integral table, and it's on there. And any integral that you're going to have to perform on the exam is going to be on that integral table. And if you don't know what an integral table looks like, you should look up your equation sheet and pull up the integral table, take a look at it. But there is an integral table that's presented, and it'll look something like this. Like it'll have a base integral. It's always going to use x as the integral variable, and it's going to use a, b's, and c's to fill in everywhere else. And it's just going to tell you what the antiderivative is of your base integral. So it exists on the on your equation sheet. Now, if we don't have paper equation sheets, it just means it's going to be loaded up there on your screen. You'll be able to tap on it, take a look at it. It'll be right there. Because what they're saying is that this isn't a calculus class. This is a physics class. And although calculus is involved, the specific antiderivatives are going to be available for you. So you don't have to do u sub and all that if you don't want to. You can just look it up on the integral table and it'll do the job for you. But you'll have to make sure you understand that in this case, b is actually negative m over c. Right? So you have to know those things ahead of time. But it's not particularly hard to use the integral table if you're not particularly good in calculus. But remember, you have a limited amount of time. You're going to have to choose where you put your time for the points you're going to get. But they've expanded it so much, 100 minutes is a long time. You should be okay. All right, let's put in our boundary conditions because that changes. Yeah. Now that we fixed that, put our boundary conditions in. This the top boundary condition is negative v naught m over c e to the negative c over mt minus negative v naught m over c e to the minus c over mt. But that t is replaced with 0 because that's our bottom boundary condition. And e to the 0 powers, well, 1. So that whole term plus the double negative there, I'm going to bring that term out front. Ends up looking like this. However, if they had given you the answer, meaning if they had said, using your differential equation, show that the position as a function of time is, they're not going to probably have that as the answer. What they're going to do is they're going to put it in a proper form where they will factor out the common term. And so they'll probably present you with an equation that looks like this and be asking you to show that this is the position function. And there's a good reason to bring this term out. Everything in here is a unitless quantity, and it's scaling your answer. Now, we see this quantity a ton of times in E&M, but we also will start to see it here a lot. It's a very common framing of what the answer is going to look like. So when you have something like this, bring this term out. It has meaning all on its own. It's going to be important meaning here in just a minute. Now, I want to go back to what we had just a minute ago because I want to talk about these two functions together. So we have v equals v naught e to the minus c over mt, and we have a position function that was derived based on that. So remember, we have now our base equations. In fact, you could go one step further and take the derivative of v and get the acceleration. Again, not a problem. Get all of your equations together, the whole set of motion equations. And taking the derivative is generally easier than taking the integral, so let's take the derivative real quick. This is going to require that we use the chain rule. So I'll bring my v naught down. I'm going to chain rule this. I'll have bring the negative c over m out front, and then e to the negative c over mt. Right? Derivative is pretty straightforward. And I'm going to rearrange this a little bit so I can pop that negative out front. I'm not surprised the acceleration's negative. We've chose downwards to be or to the right to be the positive direction. So acceleration's to the left, duh. Velocity's to the right the entire time, makes perfect sense. And position, let's take a look at what these functions actually say to us. First, is it clear to you that the acceleration is becoming a smaller and smaller number all the time? I got that decaying exponential here. So we expected the acceleration to become smaller, and it does. Also, the velocity, it's becoming 0 too, which we kind of expected. There was only a single force acting on our object. It was a retarding force. It was slowing the object down. So the object's eventually going to slow to be 0. Our position function, however, does something else. At time equals 0, this whole term is 0. Makes perfect sense. At time equals 0, our object was at the origin. So we expected our object to be at 0. But over time, as e goes to infinity, this term goes to 0, which means in an infinite timeline, x is this. This is where the object stops. How far away from the origin the object will make it before stopping. Now, I know what you're going to say. Well, the object actually never stops. Right? That's what this really tells us, right? This is a decaying exponential. It's an asymptotic relationship. So does it ever really stop? Yeah, it will. It'll be imperceptibly moving. But if you can't detect that it's moving, is it really moving? So I know it sounds like a silly question, but no, things in nature stop. One reason, of course, is that there is friction. So there's probably going to be a certain amount of that will eventually bring it to rest. Friction is a constant force. It will stop under friction. But things don't go to infinity. Infinity is a concept. So what this is telling you is that there is an answer. There is a place where this stops, and it is here. That's a location. And this is going to be a final velocity of 0, because eventually it is going to stop. And eventually the acceleration will be 0. But also, I want you to do something that I think is challenging for you. I want you to graph the velocity and the position. Let's do the velocity first. So you can either do it on your screen, you could do it on your calculator, but you should know what the shape of this function looks like. So let's start with the velocity, and then we're going to switch over and talk about the position. So it is incredibly common on problems like this for you to be asked to draw a picture of the graph representing the motion of the object. So what I'm looking for here is a velocity versus time graph. Where does it start? T equals 0, we know the object has a velocity of v0. It should be cleanly marked if you're sketching the graph. And you're going to have to sketch the graph probably for the test. So knowing where the starting point is and not marking it, you're probably going to lose a point on that. And yeah, it's a decaying exponential, and it's asymptotic with 0. All phrases and words you're supposed to know. So like I said, we know what controls this now. Making m means it's going to take longer to stop. So, and making c bigger means it's going to be shorter to stop. But now let's do the position function. So position function's here. Just try it out. Again, put some placeholders in there so we can kind of get an idea of how our object behaves. Saw better things this time. That's good. I'm looking at a function that when we start looking at it from the beginning, I know there's a lot of distraction here, so I'm just going to get rid of the distraction so we just have just this function to look at. At time equals 0, this whole exponential term here is going to be 1, which means this whole term will be 1 minus 1, which means at time equals 0, the object's at the origin. Not a surprise. That's our boundary condition. We established that from the beginning. When we let t become a very big number, this whole term gets closer and closer to 0. So when t is a very big number, this whole section of our graph, or I'm sorry, our whole section of our function becomes closer and closer to 1. But it's being scaled by this term. So I know that term exists somewhere around there, and that makes this asymptotic with this term in our equation. So I need a function that demonstrates that it's going to be approaching our asymptote. And that's why all your functions have that look to them. And this isn't arbitrary. This is v0 m over c. This is where the object's going to come to rest. Now, if I think about these variables control where the object comes to rest. So they don't not only control when the object comes to rest, as we saw over here, they control where. Does it make sense? Are these things where we expect them to be? For example, if I make the object start out faster, is that going to make it go farther? It sure is. It's right there in the numerator of that function. If I make the object more massive, it goes further. Right? It makes sense, because if I make it go faster, the force is less effective at stopping it. So it will go further. But if I increase the drag coefficient, I make it easier to stop. It'll stop shorter, sooner. Now, this all seems like arbitrary, but why do you think they put parachutes on the back of dragsters? Right? Suddenly change C so you can bring it to rest. I mean, these are all variables that are controlled in real life circumstances. And that's how that would be a velocity dependent force acting on the car. I'll try another one. We're eventually going to have to do this one, so might as well. The coffee filter. This one's going to be more complicated. There's some more complicated mathematics here, but I think it's going to have similar things to it. I want to start out with the easy stuff. The knowledge that at time equals 0, the moment we drop it, the object's velocity is 0. So when I first drop it, it will have only a single force acting on it, gravity. But the instant it starts to move, a drag force appears that is proportional to the velocity of the object. And we should do this two ways. We should do this with velocity and velocity squared. Now that means that after that first instant, the moment we have a little bit of velocity downwards, so our coffee filter is now falling downwards, there's going to be a small upward force of drag because it's got some velocity downwards. Now, these forces are unbalanced, and because they're unbalanced, it's still getting faster. So I see another stage where, again, the downward force of gravity has not changed, but because it's moving faster, the upward force of drag has gotten larger. Coffee filter's still falling, but it's falling faster now. But at the end, I am going to reach a steady state condition where the drag force and the weight will be balanced. At this moment, the acceleration is 0 and the velocity is constant. So this object's not coming to rest. It's approaching what's called terminal velocity. And we've talked about this before. But this one, you can figure out the terminal velocity without doing all this work, or without doing all the calculus at least. Because the terminal velocity occurs when that force equals 0. So mg minus cv equals 0. That's when we are at terminal velocity. So terminal velocity, mg over c. No surprises there. Make the object heavier, goes faster. Make the drag coefficient bigger, goes slower. Right? No surprises? But one thing to keep in mind is that the acceleration was getting smaller all the time until it became 0. Now, we can talk about the end portion of this. This is the end game of the problem, the fact that when we drop the coffee filter, it eventually reaches a terminal velocity. And this is how skydivers do their thing. They spread themselves out to slow down a little bit, pack themselves in to speed up. That's how they can move relative to each other when they're doing little sky dances and playing around in there. And of course, right before they hit the ground, spread out a whole lot, or else you spread out a whole lot when you splat. You got to pick which one you're going to spread out first. So it's one or the other. But of course, it's this part, what's happening in between, that we're going to have to figure out. And so that's your job, it sounds like. I think you guys can do everything up till we get to the integral part. In fact, this class should be able to do all of it because I have a lot of calculus students. So let's at least get to the integral part. So start by setting up a differential equation. I want you to go through all those steps of splitting the derivative right up to the integral part, if you would, and I'll check your work when you get there. You have all the steps from yesterday. Nothing is different than what I told you to do yesterday. You're going to start by creating a differential equation, isolate the differential, split the derivative, collect terms, and then set up your integrals, putting in your boundary conditions. Those are your steps. So we start with a net force equals MA. All right, so net force equals MA. Saw a lot of that. That's a good start. You can kind of forget everything up there for now. Making the differential equation usually good for a point. So we get that dv dt in there, and suddenly we have a differential equation. You don't have to isolate it 100% if you don't want to. I don't think it's necessarily easier or harder to do so. I'm going to do so only because in some circumstances you would have to, especially if there's a variable name there. So I'll isolate. And we split our derivative. And I see a lot of you, are skipping many of these steps because you know kind of what to do. That's great, as long as you're keeping track and know what you're supposed to do. But this gets us from our differential equation, isolate, then separate the derivative, and then we're going to collect terms, which means the t's to the side with dt and the v's to the side with v. The problem is that v is pretty much buried inside here. So the only way to get it to get it collected is to move that entire term to the right side. So I'll get dt equals m over mg minus cv dv. Now, we have to turn this into something that we can integrate, so we're going to integrate both sides. And it's not complete unless you put in your boundary conditions. At time 0, our velocity was 0, and we were looking for a velocity as a function of time. So this one, our boundary conditions are a little different than the last time, because the last time the object had an initial velocity. And this time it does not. The math is different here, though. There's certainly going to be more math here. And some of you are capable and some of you aren't. We're going to have to do more. Now, again, this you can look it up on an integral table. It's right there on the equation. Or right there on the, if you're just looking for the integral on the equation sheet, it looks something like this. It has dx over x plus a. And they say that equals the natural log of x plus a. So that's what it looks like on the integral table. So if you don't want to do the calculus, you just want to use the integral table, this is the table piece that you would use. And you're going to have to kind of figure out how to make this term look like that for the purpose of doing your integral work with the table. I hope you can kind of see that x in this case equals, unfortunately, CV, and you'll need to put the minus in there, and a equals mg. This isn't perfect because you're going to have to deal with that c as well. Now, you could, if you want to make it look perfectly like that, you could divide top and bottom of this by 1 over c. I'm sorry, multiply top and bottom of this by 1 over c, which would give you m over c over mg over c minus v. And now you've got something that looks very close to what's on the integral table, especially if you pull this out front. But still, you'll have to recognize you've got a negative sign here. You'll have to see how that plays out. And you've got your function here. So using an integral table can work, but you have to make your function look like the functions on the integral table. So how would you deal with that negative sign? Well, if you want to make it look exactly like the integral table, you'd multiply top and bottom by a negative. And now you've got something that looks perfectly like your integral table. Right? The negative sign just gets incorporated into this a. So I can say immediately that this is going to equal minus mc over the natural log of the v minus mg over c. That's how you'd use the integral table. Now, I don't want to use the integral table because this class is filled with calculus students. And you calculus students know how to use USub. But what I'm saying is if you're an algebra student and you want to gain this point, and this point may not be worth gaining, mind you. I want to be really clear. We're talking probably 1 point on the exam. So for the amount of work you may have to do the rest of the question first and maybe come back. You guys are bad at time management on the test. We've kind of seen that. And you struggle at parts that you know are going to be time consuming, and then you lose the opportunity to use the time elsewhere. They know that this is time consuming. So giving it 1 point when you have to spend 5 or 6 minutes on it, maybe go on to something else. Come back. If you have extra time at the end, earn the point at the end, especially if they've given you the answer. But let's do the math. I like doing the math. I think doing the math is a good exercise for your brain. So we'll do the math on it. I think the easiest part, just to make sure we understand, the left side of this is just t. We've done that enough times, so I don't think we have to go through all that discussion anymore. It's the right side of this part that matters. And the right side's going to take work. I mean, I could take that m out front, and that's probably a good start. That will make it a little bit easier. But this has the qualities that I'm going to have a natural log in it because it's 1 over our variable, but unfortunately it's trapped inside a function. So the way you do this is you try to make it look like it's just an inverse function by making a substitution. So I'm going to say that all of this is equal to u. This is why it's called u sub, because we used a variable u as a tradition. And now, magically, it looks like something that's perfect, except for one problem. We're not integrating with respect to u, we're integrating with respect to v. So we have to find a way to replace the du in our function with dv. And we do that by just taking the derivative of the u function with respect to v. So du dv equals, we're going to go term by term and take our derivative. So the derivative of a constant is 0. And a derivative of cv with respect to v, c is a constant, so that's going to be v to the 1 power. Remember, you bring your exponent down and then subtract 1 from your exponent. So this will be minus c times 1 times v to the 0 power. And it's a polynomial, so it's easy to take this derivative. And you guys are all calculus students just about, so I know that this is old. I'm going slow for the folks who aren't calculus students. And then that leaves me with du dv equals negative c. Now, I need to solve this for dv, so I can substitute it back in. So dv equals negative du over c. So now we substitute this into our function as well. Now, if you're in calculus, you do one more thing. You put your boundary conditions in at this point, and you right up here, you put your boundary conditions in, and you replace your boundary conditions. I could do it that way, but my calculus teacher made me do it a different way. So in my head, I do it a different way. So I'll leave it to you. Raise your hand if you want me to do it your calculus way. Okay, then I will. That means I have u, when I plug in v, is going to be just that, mg minus cv. And u, when I plug in 0, is going to be mg. So now I have everything I need to make a new integral. And that's right here. The integral from mg to mg minus cv of 1 over u times negative du over c. So I've plugged everything in to my new integral. Now, I want to take all the constants out again before I take my integration. So I will rewrite this as negative m over c, the integral of mg to mg minus cv, 1 over u du. Okay, all boundary conditions in, all constants out. So a lot of work to just say, okay, that's all just natural log now. So that's what we'll do next. Minus m over c, natural log of u, evaluated from mg to the mg minus cv. Now you still have to put your boundary conditions in and subtract, but it sounds like that's going to be a problem for tomorrow. All right. So this is where we left off yesterday? Excellent. There's not much left to do, but the next part of this actually has some challenge to it. So all you have to do is put in your boundary conditions like before. So for this, there's not a lot of meat left to do. But I do want to point out a couple of things that I think you'll screw up if you're not careful. We can skip a step or two here. We know that we're going to be subtracting two logarithms, so there's no reason not to just jump to this solution, as we're going to have to combine it anyways in order to try and get v and tease it out of there. So that is the next part, is teasing v out of this, because you need v as a function of t, although right now we have t as a function of v. So just algebra, and I think you can do the algebra. In fact, you should do this algebra, not me. So get v as a function of t, collect it as best you can, and it should take you about 2 minutes. If you're trying to time yourself on the AP exam, 2 minutes or less.
G minus mge negative c over mt over c.
So v equals
mg minus mge power negative c over mt over c.
Wait, why is it negative CT over?
All right, so there's some mistakes here. So maybe we'll clean up your mistakes. Okay, let's clean up some of these mistakes. Okay, so mg over c minus mg over c e to the minus c over mt. Right? Yeah, this is the answer. This is not how I would write it, but this is the answer. The only thing I would do different is I would factor out the mg over c. So does anybody need help from here to here? All right, so let's factor out that mg over c, because it has meaning outside of this. And if you were paying attention yesterday, you know what that meaning is. Let's go back up to here, all the way back up at the top. That is the terminal velocity. And we have to expect that to be part of our answer, because we know the object is approaching a terminal velocity. So it makes sense that after all of that algebra and calculus, we get an answer that is consistent with demonstrating the object will reach a terminal speed of mg over c. Now, we should test our boundary conditions. I always find it valuable to take a moment and test the boundary conditions, because that tells you whether your arithmetic and your algebra was done correctly. So let's start with the t equals 0 case. I put t equals 0 here. I'll get e to the 0 power, which is 1. 1 minus 1 is 0. And that means that the velocity must be 0 at t equals 0. Well, that's good. That was our boundary condition. It needs to check out. But we'd also take a look at what should be called the steady state condition. What happens when t becomes a very big number? And the steady state condition should be terminal velocity. So we put infinity in for t. That's going to be e to the negative infinity, which is 0. And that'll be 1 minus 0 in the parentheses, which is 1. So that means at a very long time, we'll get a velocity that is equal to the terminal velocity. So our function is asymptotic towards the terminal speed, which is what we expect. Any question about this as an answer? All right. So do me a service, will you? Can you give me position as a function of time? This one really favors you calculus students. You guys should be able to do this. Before you start, let's think about what our answer should have in it. And I think it's a good practice to consider this ahead of time. So let's assume that for this purpose that we're going to make downward positive, because that's what we've been doing so far. And if we consider a graph of position versus time, and let's say that the object is at the origin at time equals 0, we'll use that as our boundary condition. So wherever we drop the object, that's the origin. That puts the object here at time 0. How fast is it going at time 0? 0. So the slope of position versus time would be flat here, correct? We also know that after some time has passed, the object is going to have a terminal velocity, meaning it's going to have a constant speed. Well, how do you think we get from no velocity to terminal velocity? I'd say a concave up curve would make the most sense, right? So I think we need to have a function that looks like this. So, see what your function looks like. I'll give you a few moments. This one's a little tough, but not terrible. Don't forget to put in your boundary conditions. Most of you at least knew where to start. That's pleasant. So we'll start with dx dt. equals, mg over c, 1 minus e to the negative c over m times t. We'll begin. Split our derivative. Integrate both sides. Set our boundary conditions. And begin. This side's just x. That one's easy. I'm going to factor the mg over c outside, and then I'll start the process of doing the antiderivative term by term. So my first antiderivative is the antiderivative of 1 with respect to t. I don't think that's a lot of work. I think we all can kind of go with it's t. Now our antiderivative of e with respect to, e to the negative c over m times t, we have we have done this one already, we use just the, you could use u sub for it, or you could just use the integral table like we talked about. I'm just going to use the integral table and take whatever I have up here and put it underneath the exponential, or in this case, invert it. So minus negative m over c e to the negative c over m t. But we still have to put in our boundary conditions. And our boundary conditions produce something kind of important here. So leaving the mg over c here, when I put in t, I just get all of this stuff again. T minus, well, let's go ahead and make it plus m over c e to the negative c over m t minus mg over c times, well, I put 0 in for t and I get, well, this term just goes away, but this term goes to 1. So I will just have m over c here. All right? Look good to you guys? I'm going to disrupt this a little bit, because I will notice that if I distribute, I will get the same term here and here. So I'll demonstrate. After distribution, I'll have mg over c times t plus m squared g over c squared e to the negative c over mt minus m squared g over c squared. So now that I've done that distribution, I'm actually going to reverse it and factor out a little bit of what's there. So mg over c t plus m squared g over c squared. And then in here I'll have e minus c over mt minus 1. Now again, you would have been fine if you probably left it here, but I like this term to be exposed so we can kind of look at because this is what controls what we're seeing. It controls our function. Everything else is mostly a bunch of constants. So I want to kind of see what our function looks like, and that's the best way I think to do so. Because this thing, if you haven't figured out what I've been doing, this thing has to be a position or a displacement. It has to be. It has to be in terms of meters, because this is unitless. So whatever this is, it's got to be meters. And also, that has to be meters, right? Because we're going to have something that's going to be equal to x. So let's take a look at what our boundary conditions produce for us. T equals 0 first. Plugging in t equals 0. That term goes to 0. This term will become a 1. So the whole thing becomes a 0. So 0 plus 0. So at t equals 0, we're at the origin. We already knew that. That's great. But this isn't the same kind of asymptotic relationship. This one doesn't go to a horizontal asymptote. It goes to a linear asymptote with a slope that looks like this. Because look at the far away version, t equals infinity. Now, t equals infinity means a very big number. That just means this now dominates our landscape because it's just getting bigger and bigger as t gets bigger. But inside here, This term becomes 0, so I get 0 minus 1, and I get negative m squared g over c squared at the steady state. This is the distance. What do you think that distance is? Well, I'm subtracting it. Doesn't that seem weird? But if you go back here, remember, our object didn't start at the terminal velocity. It had to increase its speed until it reached the terminal velocity. If the object had just started at the terminal velocity, then the line would look like this. So that m squared g over c squared is this distance. How far along it would have been had it not had to accelerate to reach the terminal speed. That's that distance is. That's why you're subtracting it. So no matter where you are past this point right here where we're kind of at the terminal velocity, we're now linear. You would have been further along if you could have started at the terminal velocity, and it's this distance we're subtracting from that function. That's what that is. The transitional part here to here, I bet if you plot it, you'll get that nice curve. I'm not going to take our time to do that, but that is something you could do. All right.